welcome back to Online Statistics. I'm Naomi Lowe, and today we're covering hypothesis testing. All right, let's get into lecture. Today we are going to take everything you've learned so far, this background information, and we're going to integrate it so that you can actually start making predictions and testing those predictions. That's what stats is all about. So in hypothesis testing, we'll cover first the logic of hypothesis testing. Then we'll cover the process, how you actually perform those tests. And third, we'll look at two different types of tests, one-tailed tests and two-tailed tests. Hopefully you've guessed that these are probably the tails in the normal curve that you're familiar with by now. And then we'll talk about significance in research. By the end of lecture, you should know what all of these things mean. All right, so first the logic of hypothesis testing. When you're testing a hypothesis, first of all, a hypothesis is just a prediction. You know that probably from 4th, 5th grade doing science experiments. You create a hypothesis. It's a guess or a prediction. And in this class, that hypothesis is always going to be about a population. So you are making some prediction about a population, but we typically don't collect all of the information from our population. We collect information from a sample to answer the question about the population, to make a good guess, an educated guess about the population. So in this class, think about a hypothesis about the population. The statistical test is used with the sample to draw conclusions about that population. Now, the way that we do hypothesis testing in here, well, first, let me give you a couple of examples of hypotheses that we might test out. We might be interested in flipping a coin, heads and tails. And we go, okay, normally about 50% of the time you end up with heads, 50% of the time you end up with tails. But you might come up with this hypothesis that if you lick one side of the coin, don't try this at home, if you lick one side of the coin, that side will fall down more often than 50%. Okay? So you might lick the coin, you flip it once and you get tails, you flip it again. So you lick the tails side. Tails is up the first time. You flip it again, you get heads. You flip it again, you get heads. Again, you get heads. So we're asking, what if you were to flip this an infinite amount of times? You kept flipping the rest of your life. Would it end up being 50-50? 50% heads, 50% tails? Or would it change because of licking that one side of the coin, the tails side? So today we're going to learn how to calculate the probability that licking that coin actually had an effect on it flipping over heads or flipping over tails. One more example. My son recently participated in his school science fair, and he did his project on, it says brain right up there just to remind me about his project, but he actually was interested in playing video games, and his title was, "Do Video Games Rot Your Brain?" It was his brilliant idea because his time is limited to 1 hour of playing per day. And so he decided he wanted to try and prove that video games do not rot your brain, or they do not affect your school performance, your academic performance. And so this is the hypothesis he had, was that playing video games for at least 2 hours a day for a week straight would improve scores on a math test compared to not playing video games at all. So this was a great excuse for him to, over break, spend a whole week playing 2 hours a day. He said he had to go on and log on to this game and check and make sure the people who were supposed to be playing were actually on there and playing the game for 2 hours a week. And so he got the results of this test. Now, he was interested kind of in general, not just these few people in a sample, but he was interested in general whether playing video games helps you perform well on this math test. And so his hypothesis was that playing video games for 2 hours a day will increase or make you have better math scores on this test he created. Now, when he did this test, he found a small difference between the group. He had 10 people play video games, the other 10 didn't, and then when they took this math, they took a math score beforehand and after, and he found that the people who played video games for 2 hours a day, they ended up, the overall average of their scores dropped by 1 point. And so I went, ooh, look at, their scores decreased. And he goes, no, Mom, don't jump to any conclusions. It was only 1 point. He goes, I bet if I did it again, they might improve a point. He goes, that was probably just random, changes that we might have seen something different had we performed the same study again. So his point was that one simple little point out of a whole group of people changing that much, there could have been, maybe someone was tired when they took the second exam. There could have been other things influencing it besides just his his variable of playing video games. So he decided that no, video games do not rot your brain, that there wasn't a big enough difference or significant difference between the two groups. So here we're going to test, and I made him run a statistics test. You'll learn about randomization later in this semester. I made him run a simple test to figure out whether he should conclude that video games rot your brain or not, and the conclusion was that no, it was no different than not playing video games, and he was quite happy about that. So today we're going to learn how to test from a sample, just like my son's sample of video game and non-video game players, how to test whether that exists in the population. Do video games really cause students to perform worse in the population, or was this little 1 point just because of chance? So when we think about samples and probability, you want to think about the probability, the sample results, so like his 1 point difference, would have happened from the experimental procedure, or if the experimental procedure had no effect at all. So if playing video games, that was his experimental procedure, didn't affect their performance, could they still have moved up 1 point? Yeah. Now what if the tests had differed a lot more than that? What if the tests had differed by 50%? Or what if everyone who played video games scored 30% or below on this exam, and everyone who didn't play video games, 30, and everyone who didn't play video games had 90 or above. So there you have a big difference. You have 90 minus 30 or 60. You have a huge difference there instead of just 1 point. It's less likely or less probable you get that big of a difference just by chance, just by random differences that you would get each time you perform this study. So we're going to think about the probability a sample result would have happened. That difference, you're always going to get a difference in samples. If I measure anything, there's always going to be a subtle little difference. You're hardly ever going to find a difference of 0. It might happen every once in a while, but hardly ever going to happen. But is that difference big enough that it's not probable just to happen randomly? Is that difference big enough that you can conclude this was a true effect of whatever experimental procedure you are interested in? So that's what you want to keep in mind. Let's think a little bit more about the logic of hypothesis testing. If the probability of the sample results happening just by chance is low, so whatever your results are, if the likelihood or the probability you get that result, the difference between your groups you're interested in, is very low, that you would get that just by chance, not due to some true effect of your experiment, if that's very low, then you decide against the effect and you support the thing that you were actually interested in. So think about my son's example. If you have a huge difference between the two groups, the video players and the non-video players, then you go, ooh, the probability of getting that huge difference by chance is very low. Even though it's possible to have random things make a big difference, it's not very likely. It's very low, so you decide, it's probably not just chance. It's probably a true effect of my experiment. All right, so let's get into the process of how we test the hypothesis, what we actually do. The first step, you will want to state your null and research hypothesis. Now, both of these hypotheses are about the population, so keep that in mind. You're going to state a hypothesis about the population. Will we ever know if they're true or not? No. Will we have a good guess based on our sample data? Yes. So the null and the research hypothesis are opposite of each other. So whatever your null hypothesis is, the opposite is your research. And you always state a null hypothesis and a research hypothesis. And then when we're doing testing, we're going to always test the null hypothesis. And I'll explain that a little bit more later. So first you want to, before stating your hypotheses, you want to look at your populations of interest. And I'm going to go ahead and use my son's video game example. Let's take a look at this drawing here. I have population 1 will define as the students who play video games. So playing games, and you could describe that as 2 hours a day for a week. And then population 2 will be the group not playing games. So we have two different groups in the population we're interested in. Now he's not interested in just the few 10 people he had playing the games, but he's interested in generalizing to the population, to everyone, every child who plays video games and every child who doesn't play video games. He was hoping to prove, or to at least support, proves a strong word we try to stay away from, but he was hoping to support the idea, the notion that video games are good for you and that you should spend at least 2 hours a day on video games. So these are the two populations he's interested in. Your alternative or research hypothesis is the hypothesis that you're really interested in. Okay? So he was really interested in students playing games, or population 1 having a greater score on the math test than population 2. Now, one more thing you should think about is our variables here. We have games, which has playing or not playing. And then you also have the variable of exam score. So you have two different variables here that you're working with. Now his hypothesis is about this exam score for the two different groups of students playing games or not playing games. So think back to the types of variables. You're going to have one variable that's continuous here and another variable that's nominal or grouping, playing or not playing. His hypothesis is about this continuous variable, comparing this continuous variable for the two different groups of the nominal variable. So the hypothesis he's interested in, the research hypothesis or alternative hypothesis, is that the mean of population 1 is greater than, and this mean represents the population mean of exam scores. So the mean of exam scores for population 1 is greater than the mean of exam scores for population 2. That's what he is really interested in. That's what he's hoping to find. But we don't know if that's the case or not. He's going to collect data and make an educated guess about this population. So if this is his alternate or research hypothesis, the opposite of that, the null hypothesis, would be that the mean of test scores for population 1, students playing video games, was not greater than students who didn't play games, or equal to. So the null hypothesis always includes that equals to sign, that there's no difference between these two groups. Doesn't matter whether they play games or whether they didn't play games, no difference in their scores. So that's your first step in the process, is stating the null and research hypothesis. The null hypothesis is typically not the one we're interested in. He really didn't care if the groups were the same. He wanted to find out that they were different than each other, that playing video games helped you on this math score. But that's the one that we test. And the reason that we test the null hypothesis is because this equal sign here, you can test that they're the same, but the alternative, that one group is larger than the other, how much larger? Does it make them score half a point more than the other group? Does it make them score 5 points more than the other group, 10 points? And so we need some concrete numbers to work with. So we always test the null hypothesis. We decide if this is true or false, essentially, and draw our conclusions from what we find according to that null hypothesis. If we end up rejecting the null, we get rid of it, then we suggest that supports our alternative hypothesis. If we retain or keep the null, then we decide, nope, our alternative wasn't correct. So that's the first step, stating the null and alternative hypothesis. Let's go back to the lecture. The second step in this process is determining the characteristics of the comparison distribution. And the comparison distribution, you guys probably know, is going to be a normal distribution. That's one of the assumptions, one of the things when you're studying variables using these tests. It has to be a variable that's normally distributed. And what you know about the normal distribution and the properties of the normal curve, you know that we can look at the area under it, determine if there's a cutoff rate, if something what's the probability or the likelihood, the percentage that something would fall above a certain point or below a certain point. You're going to take that knowledge and apply it to this testing process today. So you have to determine the characteristics of the comparison distribution. Let's go back to our example here. So with our example, let's say that we know population 2, if you recall, population 2 are students not playing video games. So let's say there was past research done, and we know that population 2 Typically you don't know about the population, but we're pretending it's magic, and we actually knew this today so that you guys get the logic of how these tests work. So population 2 has a mean of 70 and a standard deviation of 2. Okay? So if the null is true, population 1 looks just like population 2. So since we're going to test the null, that's what we're going to look at, the distribution of population 2 as if it were the same as population 1, the group playing video games. So let's draw this distribution. It has a mean of 70 and normally curved. Most scores fall around the average 70. 1, 2, 3, 1, 2, 3. A standard deviation of 2. So we'd have 68. 66, 64, 72, and so on, like this. So this is the distribution that we're going to compare our sample. Remember, this is all population information right now, but we are going to take what we get for our sample 1 and compare it to this distribution. All right, we're going to compare it to this distribution. So suppose you got a sample score for someone in population 1 who played video games that scored 71. 71 here. That's the score of the person playing video games. Now you know the average for people who don't play video games in the population is 70. You go, ooh, 1 point above. Maybe the video games are helping them. Maybe, but it's not very far. What are the chances? What's the percentage likelihood that you would get a score that high from a population with a mean of 70? Hopefully you're starting to make connections between the normal curve and the properties, the area under this normal curve, and calculating probabilities. Now, if you had a score way up here, let's say your score was 80. Now you go, ooh, that's a little more evidence. This was a sample score of 80 up here from your population 1, kids playing video games. You go, wow, that's way above what we would expect to get from a population, this normal population, this population 2, where they're not playing video games. So maybe playing video games really does increase your ability to perform on this test. So that's exactly what we are going to test. Let's go back to the process here. After you've determined the distribution, you are going to then determine the cutoff. Where are you going to, how extreme do those scores have to be away from your population 1 average to decide you're going to reject the null that they're both equal, that there is no difference based on playing video games, that it's not random differences. So how far out do you have to go? Now, there have been agreed upon levels of rejection for the null hypothesis. The cutoff scores typically cut off about either 5% or 1%. Okay? It's just not exactly an arbitrary rate, but if you go think back to flipping the coin. If I flipped the coin 100 times, and out of those 100 times, I got 60 tails, 60 heads, or 60 tails, 40 heads, you might go, that could probably happen by chance, not because of making an effect on the coins. But if I 95% out of those 100 got tails after looking at it, and only 5 times got heads, you might go, ooh, something's different about that coin. It doesn't seem like it's 50-50. It seems like something's off. Now, if at 99 times out of the 100, I licked the coin and flipped it and got tails. Now you might be going, yeah, something about that coin is not weighted equally. Okay? So it's kind of our intuitive, once you get beyond that 95% rate or the 99% rate, now we're really sure that this isn't just chance. It's not just chance. And so statisticians have agreed upon this 5% cutoff rate, leaving only 5% room for error. Or sometimes if the research is really stringent, sometimes in biomedical research where making a mistake would be really bad, they don't want to say that a drug's effective and find out the drug isn't effective and spend all this money on it, or have people go through these side effects when the drug isn't really effective. So 0.01 is sometimes used for research that needs to be a little bit more conservative. So let's look at my example here of how to determine a cutoff for the example we've been working out. Now, one thing you notice, I have this little fish-like thing, alpha, at the top. Alpha is your significance level, or the area that you have to reach in these tails to determine that your sample didn't fit that comparison distribution, and you reject the null. Okay. So here, alpha is 0.05. That's our significant level, or the probability that this happened by chance that we're willing to accept. Now, if you remember the properties of the normal curve, these tails extend in both directions indefinitely. They extend in both directions indefinitely. Keep that in mind, because we can keep moving out. You might go, well, why have any error? But there's always a chance you could get a sample stat out here, even drawing it from a population like this with a mean of 70 and a standard deviation of 2. There's always a chance because that tail keeps extending and extending out this direction. So let's look at our cutoff scores. First, you have to find, in order to determine the cutoff, you need to find the z-score that cuts off your significance level, or your alpha level, that leaves, here in this case, since our alpha level we've determined is 0.05, that's always set by the researcher. It's typically going to be 0.05 or 0.01. I've seen a few types of research where they go to 0.10, but it's not common practice. So let's stick with 0.05 unless otherwise specified. So you need to find the z-score that cuts off or leaves about 5% in the tail. Okay, so you know that it's going to be somewhere up here. Remember, our hypothesis was about population 1 being greater than population 2. So now we know population 1 looks like this. This is our population 1. And we're going to compare sample information from population 2, kids playing video games. Oh, sorry, I mixed that up just a little bit. This is not population 1. This is population 2 here that we know about. Those are the kids not playing. So I'll write this up here just so we don't forget. Not playing games. And then population 1 are the kids who are playing games. And so this is a drawing of the population distribution for kids who didn't play video games, which we're assuming we already know. And we're going to compare our sample information from kids who play video games to see how far off are these kids who play video games. Now, the null hypothesis is that there is no difference between these groups. So the null hypothesis says that our sample information, or our population information for group 1, kids playing video games, is exactly the same. But we're drawing a sample from this. So you might get a sample here. You might get, a sample here. You're not going to have all of these scores. So your sample is going to look a little different than the population. But if the null was true, if population 1 was exactly like population 2, you could get a score here, 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 here. But we're going to calculate the likelihood of getting those scores. It's not very likely you get a score way up here in the 5%, unless this population is different. So first, find the z-score that leaves 5% in the tail, and you'll do that from your z-table. So go ahead and flip to your z-table, find percentage and tail, look for 5%. Now, if you notice, it doesn't have exactly 5%. It has 4.95 and it has 5.05. They didn't do every single little increment, so just take the closest one. Just pick one of those. Either one will work. I'm going to stick with the one for 5.05% in the tail, and it gives you a z-score of 1.64. So now you want to mark that z-score on your comparison distribution. So let's go ahead and draw that in. Here we have a z of 0 at the mean, and at 72, 1 standard deviation, that's a z of 1. Remember, the z-score is the number of standard deviations above or below the mean that raw score is. So here's 2. So in between 1 and 2 is your 1.64. So let's go ahead and draw that in. Maybe I'll make it red so that we can tell which one it is. So here we're going to draw in this z cutoff of 1.64. Now this cutoff is important because if your sample score falls beyond that cutoff, this direction, then you decide to reject the null. If your sample score falls below that cutoff, then you decide to retain the null hypothesis. So go ahead and shade in your rejection region. So this is your rejection region. If your sample score falls in there, we reject the null and we go with our alternative. So if our population of video game players had scores that were really high, then we would expect to get a sample score that's really high too. And if our sample score is at least this high or higher, we'll decide, you know what, it's up in that 5% rate that you would only get a score 5% of the time if indeed the populations were equal, and we'll go, no, not very likely, only a 5% chance, reject the null, that they're the same, and go with our alternative that they're different, that video games helps your score. So the next step is let's go back to our lecture, and we'll look at the next step in the process. So you have to determine your sample score on your comparison distribution. So we drew our comparison distribution, we determined our cutoff z-score, but now we have to determine our sample score, where that falls on that distribution. So we have to convert our raw score to a z-score from our sample, and then compare it to our z cutoff score. So you're going to have two z-scores, one z cutoff and one z from your sample that you've calculated that you compare to that cutoff. Okay? So let's go back to our drawing over here. And first we have to calculate a z-score for our sample information. So these are kids that play games. These are kids from sample 1. So it's a kid who we pulled out playing video games from population 1. Now, if you think about this, we can't go and give a test to every single kid that's ever played video games 2 hours a day. So we just get one kid to do it. And this kid's score is 73. This kid's score is 73. Now, we have to calculate a z-score from that number. So if you guys remember, the z-score, and we already knew the mean and the standard deviation of the population we're comparing this to, is 70 and 2. Okay? So you take your sample score, 73, and you subtract the population mean. So your score minus mean divided by standard deviation is how we calculate z-scores. You've done this before. You divide by standard deviation, you get 3 over 2. And that ends up being 1.5. So your z-score for this 73 is 1.5, positive 1.5. So this means this one student who played video games for 2 hours scored 1.5 standard deviations above the mean of population 2, or kids who never play video games. 1.5 standard deviations above. Now, once you have that z-score, the 1.5, you need to plot that on your comparison distribution. So here's our comparison distribution that we were just looking at, and I'm going to plot that z-score. Remember, z was 1.5. This is from your sample 1 score, is 1.5. So let's plot that on here. This is 1.64, so you know it's on this side. Here's 1, z equals 1. And let's draw that in. So here's your observed z-score equals 1.5. Now you get to make the decision whether to reject the null hypothesis or retain the null hypothesis. So anytime this z-score goes beyond into this rejection region, you reject the null. Anytime it's on this side of your z cutoff, you retain the null. So what do you think you do here? Correct, you retain the null. You retain the null hypothesis. And if you remember, our null hypothesis was that playing video games is no different, or it's less than, students who don't play video games. So playing video games here does not appear to improve your scores, but we didn't test, it also doesn't appear to decrease your scores. So that's how you test a hypothesis using statistics. Now that we've learned the process, you might want to practice that a few times. And I want to talk about something called one-tailed and two-tailed tests. In the test that we just did, the cutoff region was towards the right, only in the right tail, because our hypothesis was predicting that the group we're interested in would be higher than, kids playing video games would score higher than the other group. Had we predicted, which much research does, that playing video games makes kids score lower than kids who don't play video games, we would have gone the other direction, and it would have been a left-tailed test. We would have had our cutoff region, the bottom 5% of our normal distribution, instead of the top 5%. Now, there's also such thing as a two-tailed test. And in this class, unless we specify, just assume that you're doing a two-tailed test. A two-tailed test is a test where you use both tails. So your null hypothesis is that there's no difference between the groups. So maybe there's no difference in scores between kids who play video games or don't play video games. Alternative, that's the opposite of that, is that there is a difference between the two groups' scores. So it doesn't matter whether the kids playing games score higher or lower, you're just testing both directions if there is a difference. Now, when you're testing both directions, you have to take your 5% cutoff rate and divide it in half and put 0.025 or 2.5% in each of those tails. And here's an example. If we go back to the drawing board here, here's an example of different tailed tests and the hypotheses you would make with a right-tailed, left-tailed. Those are both one-tailed tests or with a two-tailed test. So here we have a right-tailed test hypothesis. The alternative or research hypothesis is that group 1 is greater than group 2. Kids playing video games will score higher than those who don't play video games. So your null hypothesis would be, go ahead and write down what you think it is. It would be that group 1 is less than or equal to group 2. That's your null hypothesis. And in this type of test, you're only going to reject the null up in this top region. So you cut off the 5% here, or the 1%, depending on what your alpha level is. A left-tailed test, which is also a one-tailed test, it's the opposite prediction. Group 1 is less than group 2. And so if that's the case, what do you think the null hypothesis would be? Go ahead and write down what you think it is. The null is that population 1, the mean, is greater than or equal than population 2. And the way you would test this is the rejection region is down here, only if group 1 falls below that cutoff rate. So you cut off the 5% or the 1% on this side. Now, the two-tailed test, you have the normal curve, and your alternative or research hypothesis is that group 1 is not equal to group 2. So you might not know whether playing video games will improve your scores or decrease your scores, but you think it's going to have some effect. It's going to do something where the two groups are not equal. So their alternative hypothesis is they aren't equal, so you're going to test both sides. Go ahead and write down what do you think the null hypothesis is here. Remember, it's the opposite of the alternative hypothesis, so it's mu1, or mean of population 1, equals mean of population 2. So it's that they're both identical, they're both here, but then the further they get apart, the further your score is from there, in either direction, this direction, or this direction beyond your cutoff scores, you will reject the null. So now your rejection region isn't only on one tail, as these two tests are, but in both tails. If your score falls below this line right here, you'll reject. If it falls above that line, you'll reject. For this class, stick with the two-tailed test, unless it specifies that you're doing a one-tailed test. The reason you would do a one-tailed test or a two-tailed test is typically because if you have past research that suggests that it's only one direction, this direction, or this direction, then you go with the one-tailed test. But if you're doing exploratory research or you're not quite sure which direction the test is going, you want to stick with this two-tailed test. And in fact, there's a lot of controversy among statisticians whether one-tailed tests should be used at all, because it gives you a larger region. You have the whole 5% here, where here, if you're using a 5% significance level or alpha level, you only have 2.5% here and 2.5% here. And so they said you're going to reject probably more often here than you would on the two-tailed test. So you're less conservative with the one-tailed test. And so some statisticians think that you should always use a two-tailed test, because you wouldn't find an effect that even if you weren't looking for something, say with my son's test like this, had the scores been way down here, we wouldn't have rejected the null, and we would have said, oh, the groups are the same or less than, we don't know. And so we wouldn't know that video games decrease your scores unless we were doing a two-tailed test. Okay. All right, so back to the board. Here's an example of what you do when you have a two-tailed test. I just drew it on the paper for you, but if you're doing a two-tailed test and you want a 5% alpha or significance level, you just take that 5%, divide it by 2, and put it in both tails. Then when you look up your Z cutoff scores in the back of your textbook, you need to look at the 2.5% in tail. instead of the 5% in the tail. If you're doing a 1% alpha rate, then you have to divide that 1% by 2. Each tail gets 0.5%, and you have to look up that 0.5% in your z-table to get the cutoff scores. All right, so when significance is reported in research articles, what they mean by significance is not that what they found is important. Okay, so for stats for this class, for this semester, wipe out what you know about significance. All significance means is that you rejected the null. Okay, so if they reject the null, they say it's statistically significant. A lot of times they put a little asterisk up for significance, or they'll put sig or ns for not significant. I laugh because the new building they just put in, the natural sciences building, it has this big NS on it. They named it the NS building. So I think now they should, the new building that they're building right now should be called SIG. So they have an NS and a SIG. I told that to a biologist the other day and they just looked at me like I was strange. I think it's about statistics a little bit too much. Anyhow, significance means that you rejected the null. So it means that the results of your sample are not likely to have been found by chance. The probability of your sample difference is not likely due to chance. It's likely, if it's not due to chance, due to whatever you're interested in, your alternative hypothesis. So it's support for your alternative hypothesis. Now, it doesn't mean that whatever effect you found was a huge effect. You can have something that's significant. We could find that video games do change your scores. They decrease your scores on a test, but they only decrease scores by 0.5 point. That's not that big of a deal. Or you could find video games do decrease your scores and they decrease your scores by 20%. So significance has nothing to do with how big of a difference you find in your groups. It just has to do with your conclusions about the population based on your sample information. The conclusion that whatever this effect is, whether it be small, big, moderate, that this effect is not likely due to chance. It's more probable that this effect is due to some alternative hypothesis. Sometimes you'll see in literature near significant trend. Because we use that 0.05 cutoff, if you had a score that was slightly below that 0.05, say it fell at 0.055 in the area in the tail, you would still have to retain the null. But it's a little bit arbitrary. And so sometimes if you get something that falls at that 0.06 level, in between 0.05, the 5% and the 10% in the tail, they'll typically say that it's approaching significance or near significance or a significant trend. If something's not significant, they'll typically just say NS. There won't be an asterisk by it. You also see P is less than 0.05. And this just means that they passed that 0.05 area in the tail and they rejected the null. It also, the P stands for probability. And probability, let me draw an example here of a curve. And if you have, here's your 0.05 cutoff, now your 5% in the tail. You would reject if your score fell in that region. Now, if your score falls right on this edge, that's typically when they say that something is approaching significance, not quite significant. Oh, that stinks as a researcher when you get something so close, but not quite there. But suppose your stat fell here. Okay, you reject the null, no problem. But suppose your stat fell way out here. Okay, now it's really different to that comparison distribution. And there's no difference between this significant star and this significant star. So typically they'll list a p number, and that p value, the p value is the probability that your result, whatever the sample result is, occurred by chance only. That it's just it's because you got a sample out of a population that was off, that it occurred. And so this probability up here, only 5% of the time will you get a sample beyond this point. Only 5% of the time will you get that with the population with this mean. Okay? So the probability you get a sample beyond this cutoff is 5%. That you get a sample beyond that if the null is true. Okay? Now, what's the probability you'll get a sample this far or above if the null was true, if this was the true mean in the population? it's less than 0.05 because you know the probability, if this is 5%, this is going to be less than 5%. And you could actually look up this score. You look up the score and you find the z cutoff and the area beyond that score, and that's your p-value. It's the area beyond your observed test statistic or score or mean, whatever you're putting on here. It's the area beyond that that is shaded in. So the likelihood of getting a score that value or more extreme further in the tail. So a lot of times they'll list p-value. They'll say p equals 0.001 or 0.021, and that way you know exactly how much area was left beyond that the statistic. All right, and here's a table. This is just an example of significance in research articles. If you notice, there are little asterisks, and down at the bottom, there's a key. There's one asterisk if the p-value is under 0.05. There are two asterisks if the p-value is under 0.01, and there are 3 if the p-value is under 0.001. So that gives you an example of how far out your test statistic fell. And the smaller that p-value, the less likely you found that extreme of a score just by chance that when the null was true. And so you go, oh, not likely to happen by chance with the true null. It's more likely that the null isn't true. You go with your alternative hypothesis. They kind of use this as a decision making. If you pass that 0.05, significant, go with alternative. If not, keep the null, your alternative, you don't have support for it. So that's how you read the research article. You can see they're comparing friendship for males and females. And you can see at the top, friendship quality was significantly, because of those asterisks, different for males and females. 2.49 for males, so it was higher for females. Friendship quality was higher for females, significantly higher than for males. It's not likely this was just due to chance. It's likely that there are different friendship qualities between males and females. Loneliness at time 1 in adolescence was also significantly different. Males were significantly more lonely than females. But then if you go down to emerging adulthood, it looks like friendship quality is still significantly different. Females still have higher friendship quality or report higher friendship quality, but loneliness is no longer significantly different between the two groups. So there's no asterisk on loneliness at time 2. So that means that maybe the males who were lonely during adolescence, even though they didn't change their friendship styles, they found other things to do and they don't need those quality friendships anymore to not feel lonely. Okay. So that's where we will stop for today. It's been a pleasure. Hopefully you grasped this. If you didn't understand the things in the past chapters, you'll definitely want to go back and review, because all of the concepts we've covered this far we're just going to start taking off, and you really need to know those very well to be able to apply them to these testing methods. All right, it's been a pleasure, and I look forward to seeing you next time.